So the next speaker would be
I'm Snashish, and I'll talk about investigating the UV spectral properties of early time and near peak Taiwan supernova. So before we get started, I need to explain what is early time and what might mean. What do I mean about near peak? All right. So this is the light curve of a Taiwan supernova. This is not really a real one. This is the peak. This is -5. This is +5. So this, if we do an observation within this period, this 10 days period, we call this near peak observation. And anything earlier than that, from -5 to -18, we call it early time observation. So the aim is simple. I want to investigate the UV spectral properties. That is there any difference between observations which are done here and here? So I have some objects for which we have for which there are some observations at near peak and some observations at early phase. Some of them also have like overlapping. And the answers which I want to get is that can they tell us something about the mechanisms or anything about their host galaxies or any kind of relationship which we can use to improve them as standard candidates in cosmology. So the question is, why do you expect there should be any difference in these two phases? So the important thing is that why do you expect there to be any difference between these two phases? Why this is important? So early phase, less than -5, -6, -10, whatever. What does, if you do an observation in that phase, what does that tell you? Like during the early times, the spectra which you take is sensitive to the outer ejecta composition. And during this phase, you can find some material which is unburned because it's outer ejecta, some material might not be fully burned. So you can get some carbon or oxygen features in your spectra. And this can tell you about the explosions and mechanism of how that explosion took place. And there are some theory papers which claim that the spectral features, the flux and everything, it is sensitive to the metallicity of the progenitors. I put some brackets because this is in theory, not in, this has not been confirmed with observations. And during this early phase, there could be, if there's a CSM around that supernova, there could be some shock interaction with the CSM, and that would those images can come in your spectra. So these are the three things which is very important for early phase. All right. Now near peak. What do you get from near peak? If you do an observation at near peak, you get to know something. You get a correlation between the delta M15. Delta M15 is a parameter used in Taiwan. It means that how much. What is the difference in the magnitude from the peak to 15 days after the peak? All right. And these kind of parameters are used for improving the luminosity correlations and to make the distance indicators much more precise. And previous studies have found that it is also related to the metallicity. So metallicity is a very important thing here because in both cases it is very sensitive. But in one case it's theory, not confirmed, but in near peak it has been confirmed. So this is what I want to do here. I just want to check if these are correct or if there's some other things missing. All right. So we got data from SWIFT. SWIFT is like space telescope, and it has been launched like 2 decades ago. And the primary focus of SWIFT is to see transients, right? Now because of that, it has to have very fast turnaround, right? And that's why it doesn't have a split. So it has an instrument called Prism. Prism is an instrument which uses a combination of prism and a grating, right? Now, because of that, this object, the spectra which you get is not a very. It has a lot of contamination because you get light from nearby sources, the host galaxies, and what previous people have found that it is very difficult to decontaminate the spectra. Alright? So I show you a picture of what it looks like. In perfect world, you want only the first order. But in addition to that, you get all this contamination, the zeroth order, the host first order. Now, what we have done is that we have improved the background decontamination method, and we are planning to release the script with this paper. It's not out yet, but it has been taken care of. All right. Now I talked a lot. Now, what I'm going to do here? Objectives. What I want to study here? I want to study the light curve. I want to study if the UV spectral features in both phases does that correlate with the decline rate? Because now we have more samples. So previous studies have used smaller samples. Now we have more samples. So let's see if those results stay or we find something different. And I also want to study if those spectral features they correlate with the host physics properties: mass, stuff emission rate, age, metallicity. And this I haven't yet completed. So we're going to study properties with the ejector velocities, silicon velocities, calcium velocities, and we're going to produce mean spectra, which we can use. Because those mean spectra will be grouped. So for delta 15 or any parameters, we may have mean spectra for different parameters. And then we're going to compare this lab I finished. So we're going to compare the UV spectra of subtypes. The one before me, he talked about the light. So we're going to see if the UV spectra features are different for this kind of peculiar type 1H. And also there are some supernova which have a bump. I'll talk about this. Some bumps in the light curves. So the idea is, does these have any differences in the UV spectra which we can use and we can tell us, okay, if this feature is present, then those can be defining traits of this kind of subtypes. So this is the game. Alright, so just straight to the results. So this is with the delta 15. So this is a much bigger sample. So this, okay, first of all, so we have two panels here, right? The one on the right. The one on the left, right. So for you it's left and right. So the one on the left, the y-axis is F. This is just a UV flux ratio, right? In simple words, it's just UV flux divided by the mean UV flux divided by the mean optical flux. Okay, so this is mid UV, this is mid UV, and this is near UV, right? Simple. And essentially we have delta 15. This is just a parameter of type 1N. So we have 2 points, two types of points, blue and red. Red one are the early type, -5 to +5, right? And blue ones are the early type, less than -5. What we find here, we find a 2 sigma correlation between the mid UV flux ratios with the delta 15. This is very important because this we can use in both cases. So, but here the trends are opposite. So this is another thing which we have to understand why this is negative, why this is positive. So, but what you find here is that, and here it is 4 sigma correlation, right? So what we find here is that these kind of correlations can help you understand more about the exposure mechanism. Why? Because previous studies have found that this parameter is correlated inversely correlated with the nickel production. And we know in nickel is undergoes decay, and it powers the light curve of type 1. So it's the main element which produces light, which gives the brightness of type 1A. So it gives the luminosity. So if there's a parameter which correlates with that parameter, so we can use these flux ratios as a way to understand the mechanisms and to understand more about the type 1X and how it powers the exposure mechanism, how much nickel is formed, all those things. The y-axis is the same. The x-axis is log. This is just metallicity. So this is okay. What is this? This is so we first do the host photometry, then we fit the SAD of the host, and we get some metallicity. This is the metallicity of the host galaxy in which the supernova is found, right? Same, but we don't find any correlations with the near UV. If we find some correlation with the mid UV, 2 sigma correlation with the mid UV. Now, what does it mean? First of all, two things. First of all, in theory people have said that these metallicity and flux ratios should be correlated for the early type sample. But we find that the blue ones is early type, the data is for the early type. There is no correlation for the early type. Correct? So what does it mean? It means that whatever the theoretical assumptions have been made, it is not valid for this kind of in observations. I'll go fast. The age. This is the most important part of our paper. We find a 5 sigma correlation with the age. What does it mean? It means that more older. If the white dwarf is older, it means it's cooler. If it is cooler, it's more denser. If it is denser, it produces more IgE. IgE is intermediate group elements, and those elements have a tendency to suppress UV features, right? So this is how we explain this trend, because this is 5 sigma trend. So what it means is that if you have a supernova in an old galaxy, it will produce less UV flux because of the reason I just mentioned, because they are cooler white dwarfs and they are more stable, more denser, would produces more nickel 58 on the surface, and that can suppress UV flux level. Alright, so now okay, so there are some supernova which have bumps, or these bumps. These bumps are caused due to many kind of like scenarios like shock interaction or double detonation or any kind of scenarios. Now what you want to do is that we want to find out if there is some UV features which we can use to differentiate this. We find that so the red ones are the bumped supernova. We find that they don't show UV excess. So now in theory it's proposed that if the supernova has shows bumps, then those supernova tend to produce more flux, more luminosities for a certain period of time. But we find that their UV flux does not show that. So we rule out CSM interaction as one of the ways by which we can get those kind of bumps. Peculiar type supernova. So the main idea here is to see if a supernova is peculiar, does that show any UV feature which is different from normal type 1A? So there are the red profiles which you see here. This tells us that the red one is 03 Fg like. They are more overluminous than normal type 1A. We find that they have a higher UV flux. 91 Bg are subluminous. We find that they have lower UV flux. And 99A is also overluminous, but it's not so overluminous as 03 Fg light. And we find that they also have like somewhat higher UV flux. Thanks. I'll take questions.
So I missed the earlier part of the talk. So did you consider a new collab for that?
Well, yeah. We're doing for the whole galaxy and also for the Milky Way. We do MCNC.
Very nice question, but I just wonder if you want to compare early phase and the late phase.
Yeah.
You can just take the specific source which has the both the
We have, yeah.
I think we combine for example some sources simply early potential.
Yeah.
Your source
No. So there are some sources which have observation in both, but that's very few. Only for the nearby ones, because people don't usually because the thing is that if the supernova is type 1A, we just need one spectrum. We don't spend too much time on that same object again and again, unless it's interesting or it's nearby. Then you can spend more time on getting multiple spectra at multiple epochs. So we only have like few objects which are both in both the epochs. Yeah, it's a mixture.
So let's thank you.